Hello again. Tonight we're going to talk about a recently published survey analysis, and they think they found initially what they thought was going to be the ninth planet of our solar system, but it turns out it's not exactly where they thought it was. So maybe it's not the ninth one, maybe it's the 10th one. They still have to keep looking for the ninth one, but we'll get into what all that minutia is. So humans have this funny notion that something doesn't exist until we confirm that we've observed it. When they say something like a new asteroid, planet, comet was just observed for the first time. Okay, it was just observed for the first time. It's not new. It could have been there millions of years, longer than the existence of life on Earth, but humans only recently confirmed seeing it for the first time. So it's not new, it's just new to us. Old for the solar system, new only for humans. That's because we look for things, and until something has been observed, there's just this kind of background, don't know that it exists, wouldn't care to find it if it existed, but that's just human nature. So when we first went looking for planets in the solar system, it was pretty easy. Just look up all the nearby and brighter ones and even larger ones like Jupiter and Saturn. Those were easy to spot. You could see them as wanderers in the sky all the way back into the BC years. So the last one to be visually discovered was Uranus in 128 BC, but they thought it was a star because it moved so slowly. It wasn't recognized as a planet until 1781. So even when we see something, can't be a planet, doesn't move really fast, just our way of categorizing things. Then we switched to another approach, which was predictive observations. We would take things that we had found and notice that their orbits weren't quite uniform all the way around the orbit. They had like a bump in the orbit. And the bump in the orbit was probably because there was another large object near to it in its orbit that caused its orbit to be perturbed, as they say, or moved a little bit. Neptune was originally identified as a star in 1612. And then when they noticed perturbations in Uranus's orbit in 1845, they concluded must be a planet. Took some time. And the last one that I guess in the newer era that we did with better instruments, big telescopes inside of domes on mountaintops, was visual observing of Pluto as something that we noted as having affected Neptune's orbit. So 1930, we found Pluto. We didn't start out thinking it was a star. We actually were looking for another planet, and we found this thing, and we tracked it, and it was a planet up until the International Astronomical Union said, we can't call all these things planets. Why don't we call this one a dwarf planet? Because it hasn't cleared out its orbit. Pluto doesn't care what us silly humans call it. It was there before us, will likely be there long after us, and certainly long after the sun ends its existence and shrinks down to a white dwarf. But the way we find these things through predictions is because we had advancements in mathematics and astrometry, or the study and prediction of orbits and positions. So without the advancement of math and astronomy, we wouldn't be able to make the predictions to find the things that are so distant and tiny that we can't see them with the naked eye. Well, when we take an orbital prediction, it tells us the orbit, like the elliptical shape of what we think the orbit of that object to be, but it doesn't tell us where it is in the orbit. It just tells us what the orbit is. So with a predictive orbit, we have to look around the orbit to find the object or to spot it. And then once we spot it, we have to spot it a total of at least 3 times before we have a clue that the predicted orbit is very close to the observed orbit. Space is big, things are moving around all the time, and when you're that far out, you move very slowly and might be mistaken for a star. So when we look at a place in the orbit, If we don't see it, it just means we didn't see it. If we continue looking around the orbit, as we're advancing in our view of the orbit, it may actually be following directly behind us. So it's following behind us and we're not seeing it. So that's just, it's where it is. It's not where you're looking. So, as the saying goes, I was looking over here because the light was better. Knowing where and when to look is a huge factor in a predictive observing request being successful or not. So the new normal approach is retrospective presumption. And what that means is instead of just looking around in the sky for where things might be, that's a lot of observing time. That's a lot of telescope or deep space satellite observing time. Well, we've been taking pictures of the night sky at pretty reasonable resolution for decades, and we've been recording it. And some of those images that were originally on glass plates have been digitized, and they're in computer cloud-based archives. So maybe you can write some artificial intelligence or smart software tools to scan through all the survey archives. If you look at the same place in the sky, you'll see something moving through it. But if it's something that's moving with you, you have to look at the whole sky and see what of those things are galaxies and stars and nebulas, and what of them have moved a little bit over a long period of time. And so that's how they find these now, is they look through entire archives at not just one spot of the sky, but the entire sky that's in the survey. And then they compare it to another survey like 23 years later and see if all the same things are there. And if anything moved from this survey scan to this survey scan, that must be something in orbit around the sun. So that's how they're finding things now. But as they look farther and farther out, the items get smaller and smaller quantity of pixels in the images, and the amount of distance they move is even less over a short period of time. If you went back and looked at an object that far away and you looked at it, let's say every other year, you might not even see it move. You may have to look every decade in order to see it moving at all. So they're now out to the two different surveys, 23 years apart. They found something moving. They've only got 2 observations. They need at least 3 to be able to create an orbit. So they're presuming that this retrospective presumptive object is Planet 9, which one team has been looking for over a decade. And this new team hasn't been looking that long, but they've been looking at stored data that's 23 years apart. So it's much easier to look at stored data for things. Think of it this way. When you have a survey catalog and it has millions of objects in it, you have to remember the position of all those millions of objects over that 23-year span to see if anything's moving. So it's not just they suddenly discovered one thing moving. They found lots of things moving, but then they had to go back and analyze why the AI tool said, I got one. The 2 historical observations that this recent publication studied was IRAS and AKARI. These were 2 Earth orbiting infrared survey satellites. So this was back when we didn't know what all was out there in space, and we're just going to catalog the entire sky as much as we can. So we put satellites into Earth orbit that were infrared sensitive, because we knew these things called red dwarfs, probably a lot more of them, brown dwarfs, orange stars, and they don't show up easily visually, but they do show up in infrared. And all the brighter stuff shows up in infrared. So we'll look at infrared. So these 2 survey satellites were looking in infrared. They were about 23 years apart between IRAS and AKARI. AKARI was actually from JAXA, from the Japanese Space Agency, and IRAS, who I believe was NASA or EU, I forget which. They looked through both surveys using computer software, and that's how they found this object. Why would you be scanning these archives? Isn't it much more effective to just put in an observation request and get time on, the Hubble Space Telescope or the James Webb Space Telescope? Here's the thing. Professional astronomers put in requests months in advance of when observing time is actually allocated. They have to wait months to see whether or not they're approved. If they're approved, they get a time slot. The instrument will point where you want it to point at this date and time for this amount of time, and you'll get an observing window. And if something happens, like they've got a temporary equipment malfunction where the equipment has to be recalibrated, or something like a comet or a near-Earth asteroid is more serious than what you want to observe, so your observation window gets bumped, try again, a year from now when the window opens again. Booking time is really something you only want to do when you know what you're going to look at and when you're going to look at it. Sometimes, like, you have to go to the telescope, even though the images might show up by email as attachments, in order to talk to the technicians to make sure that the telescope and the camera are going to do what you expect of them. You have to book travel. You might have to go from, I don't know, the UK to Hawaii, including the cost of your travel, your lodging, your food, your clothing, because it's a high mountain. It's cold up there. Just to talk with the technical team before your actual observing time is approved in the queue, just to make sure that you know what you're looking for. Is there a way that you can avoid all that stuff? Well, if you're looking through archival image data, whether it's from a survey or a specific looking at a particular location in the sky, that saves a lot of money. First of all, you can do it right now. You don't have to wait months to get a time slot. I actually have access to the Space Telescope Science Institute's MAST archive and have looked at things in there. And it's fascinating. You have to know what you're looking for, what instrument, on what spacecraft, or what observatory, and you can narrow it down. And then, do you want the finished image? Do you want the intermediate ones? Do you want the calibration images? And you can look through all of that stuff. And there's no cost to using it. It's sort of your tax dollars at work. So if you're a US citizen, you can request access to MAST and they'll give you a login. It doesn't cost anything to use the equipment that took the images because you're not doing it live. It's already in the archive. In fact, the two instruments that they used, those have already been decommissioned. Those are like not taking images anymore. The travel expense is gone. You can use AI assistance and software to scan the data for exactly what you want. And you just sort of write the software, do a couple of test samples, get a false positive, a false negative, and make sure the software is working. And then you just let it munge on the data for maybe months at a time, because there's a lot of data out there. And it comes back and goes, found one. And then you look at what it found and see if it's really what you're looking for. Using software to scan survey archives is a very much less expensive way of doing it. It's faster because you get immediate access pretty much. And you just have to wait for the software to go find what you're looking for. And if it finds it, it finds it. If it doesn't find it, then you probably want to look at your software algorithms to see if it's letting things slip through the cracks. Once you think you've found something, then you want to step it up to, instead of survey images, you want to look at more studies, like ground-based or infrared-based optical telescopes. Or you can look at other things that are more recent that have just started storing their data in places like MAST, which is Gaia. But Gaia was looking for galaxies, but it's still got to see stars. So things that are near in orbit around our sun would appear in the Gaia, not the final images, but the raw data. So you may want to search the raw data more importantly than the finished goods. But once you've found a spot in the sky and you have a guess at what its orbital characteristics are, you can then look at other archival data to see if it was there as well. So if you looked in Gaia's archive and you found it in Gaia and you know where it was at what time, you can probably go back and look in the archives of the Spitzer Space Telescope, that was infrared, SOFIA 747, Aerospace Infrared Telescope, and the Hubble Space Telescope, which also observes in infrared. So if you found it in a Gaia image on a particular date, particular time, particular part of the sky, then go to these other archives. You don't have to request time. You can just look it up in the data and see if it's also confirmed. So now you could have not just one observation, you could have 2 or 3 observations of the same place, same date, same time. And now you can look at other observations. So leave your AI software running and see if it finds another found one. And then go back and repeat this again. Look in other archives and then use that to spot in the same place using other instruments archives. Once you have 3 points, you can have your curve and start to judge at a minimum level the orbit. I think you need at least 5 or 7 points, something like that, to truly calculate a precise orbit. But at a minimum, 3. Not 2, not 1, 3. Do look internationally. Don't just look at like NASA. Go out, look at archives that are available to you if you're in the EU, the European Union, or Japan, or even China if you have access to it. So once you've got an orbit and you know where you think it's going to be at a predicted time in the slightly distant future, you can now start to schedule your orbital, your observational slot on real telescopes like the Hubble Space Telescope and the James Webb Space Telescope. So, once you think you know where it's going to be, confirmed by your orbital prediction, you can now use real live instruments to look at new data, focus specifically on it. And why just look in the visible and infrared bands? We have these things now called very long baseline interferometry radio astronomy. That's where you take a bunch of radio telescopes and they, in software, glue it all together, make one big telescope, and it can look at the sky. And they also have archives of data. A lot of their archives are looking at things like pulsars and quasars, which are black holes emitting like pulsar beams, nebulas, things that emit lots of radio. But another thing that they're looking at is the cosmic microwave background sky. And if you're looking for something in orbit around the sun and you look for it in radio, and you have a high resolution VLBI image in radio, you may see a hole, like a place where the radio signal didn't come through. And that's because it got blocked by that planet way out in our solar system that made a little no signal here hole. And there's this other thing called frame dragging. If it's a planet the size of Neptune, even though it's that far out, it'll actually create a gravitational well around the planet. And as the planet moves through space, that well will extend out to like a teardrop shape, which means that instead of it being a nice, precise, round hole in the microwave background, it'll actually be a little teardrop shape. So not only can you see where it is, how big it is, you can also tell how fast it's going, what direction it's going by the shape of the occultation hole. I don't think they've tried that yet. And then, is this planet 9 or planet 10? The thing that they thought they were going to go looking for, the planet 9, isn't in the place in the sky where they found this thing that they believe is a distant in our solar system planet. Maybe it's planet 10. It's larger than Neptune, which is larger than Earth. So it's big enough. So what do we do about planet 9? I say that we leave the gap there. So we might have found a 10th planet, but keep looking for the 9th planet. Leave that hole in there. And once we find a 10th one, we're going to have to change that nursery rhyme we use to remember the names of all the planets to accommodate not only the 10th planet once we give it a name, but the gap until we find the 9th planet. But, when somebody says, we can't call all these things planets because then students in school would have to learn 30 plus planet names. I really feel sorry for them because, they increased the number of elements in the periodic table from 104 to 115. And students studying chemistry and physics still have to be aware of all those elements, know how to spell them. Some of them even get to the point where if you're in your second semester of chemistry, you may have to even recall the atomic weight of all those elements. So no empathy for 30 planets. So if this thing is a Neptune-sized Kuiper belt object, that means it would not have cleared out its orbital path. And once it gets recognized as sufficiently large to be spherical and it's orbiting the sun and it's not a moon, it's at least a dwarf planet because it's in the Kuiper belt. But using the term dwarf to identify something much larger than Earth, about the size of Neptune, I think the International Astronomical Union needs to revisit their use of the word dwarf and maybe refer to them as Kuiper belt embedded planets or something, and not have any moniker regarding the size of the planet that they find. Because if they're just now finding this new way to find them, they could find even more of them farther out. If they find them, let's say, farther out, and they happen to be much larger than Neptune, approaching the size of Jupiter, they're just very dim, very cold, and very far out, which is why we haven't discovered them yet. They're not new. They've been there for a billion plus years, but they're just new to our knowledge. Don't forget to look when not looking. This sounds weird, but a lot of the images that these telescopes take are calibration or test images or target field alignment images. They're not looking for anything other than what they're looking for. So in the case of calibration or test images, they're looking to make sure the hardware works, that it produces values in the expected range. But what it's looking at, they don't care. But they do store that data. Target field alignment, they're trying to frame a particular area of sky where there's like a nebula that they want to look at or something. They don't care about all the other stuff because they're going to crop that image down to just look at the nebula. A good example of this is the pillars of creation, which are very tiny within the Eagle Nebula. And the Eagle Nebula itself is not that large. So when they take an image with a wide field camera, all of the stuff around the Eagle Nebula, it's just stars. But if you go back and look in the archive, you may find, well, look, there's a planet there that we didn't know about. So look in the archive data of calibration and test images and target field alignment images for these additional objects. And don't just look in the finished images, look in the raw, non-colored images, because you may find in the monochrome or grayscale images, there are things that get washed out when you colorize the image. Given that these calibration or test images or field alignment images are considered raw, unqualified, uncalibrated, use them to find where you want to look. With the more serious images, calibrated, qualified images, in order to find something that was there all along that you just noticed. In summary, the universe is a big place. The solar system, solar orbit, is also big, and we're finding things farther and farther out that are still in orbit around the sun. If an object is really tiny and it's really far out, it may not be able to hold on to its orbit. But if an object is large enough, even though it's really far out, it could probably have enough gravitational relationship with the sun to hold its orbit. So as we look out farther, we may find not just small things, we may find some large things. We need to look farther out. And when we look farther out, the object we discover, may only be a handful of pixels in an image. So we need to look at more images. And using automation to scan survey archives is a good starting point. And then once you've kind of narrowed it down, you can look at other, not just surveys, but other observations. And don't forget it's not a big telescope on the Earth and it's not a telescope in space. It's a telescope that flew through the skies looking in infrared, SOFIA. And remember, you can also look at radio for radio occultations of the microwave background. You never know what you might find until you look. And I can't wait for the moment we go looking for and find Planet 13. Wonder what we'll call it. Lucky. Let's call it Lucky. And then if you're curious as to how they found Uranus and Neptune and Pluto, and then this publication may be looking for, is it Planet 9 or Planet 10? And then the two telescopes, the IRAS and the AKARI. And then if you're curious, you might want to look things up. There's the MAST archive at the Space Telescope Science Institute. And then for those that want to look in SOFIA's data is not in the MAST archive because it's not a space telescope. It was an aerospace telescope. So it's associated with the IRSA, which is infrared astronomy, not necessarily from things out in space. So getting back to our astronomy roots, no longer talking about far-fetched technology or photonic propulsion or things like that. Comments? Question?
You talk about AI doing the searching.
Yes.
You need to go as far as AI. Seems regular computing could compare photos and plates and
well, if you remember the first images of a black hole, they didn't know what to expect. So they trained software, AI software, to look for the unexpected. And the way they did that was they gave it thousands of images of things that weren't the black hole. So they would feed it pictures of like dogs and cats. A dog and a cat are not the black hole. So if you see one of those things in the archive, unlikely, that's not a black hole. Same thing in this case. What does a very distant planet in our solar system look like? It looks like a handful of pixels that maybe only one or two of them are bright and the rest of them are varying levels of dim. But how do you know that's not a star? Well, if you remember where every one of these blobs are, millions of them, and then you look over a period of time, you know where the stars are going to be. They have regular movements. You know where the galaxies and the nebulas are going to be, although Gaia has seen that those move very little, but they move over time. So you use the AI as you train it to look for things that are different that move. Now, yes, you could write a software algorithm that does that, and they've actually written software algorithms that did what people used to do. The way that people would spot an asteroid or a comet is they would take a picture and then 2 days later take another picture. And then they would have both these pictures show up in a viewer, and the left eye would be looking at one picture and the right eye would be looking at the other picture, and you would blink one of the images, and that would create an image in your brain that would see the difference. All the stars that didn't move, your brain would wipe those out, and the star that did move, your brain would point it out. So it's called a blink comparator. People used to stare into instruments and do this for hours on end. Nowadays, they have computers do it. It's not AI. It's just simple pixels that are bright, weren't there, now they're there. Were there, they move. And that's pretty reasonable for finding asteroids and comets because they're closer in and they move much faster. But when you have to scan, terabytes worth of image data on 2 different satellite programs, that's too much for a human to look over individually. And you want to do it kind of in a shotgun manner. You don't want to just start at the beginning and look through all the images, because that would take years. What you do is you randomly start up multiple processes, and they're all comparing their results and saying, hey, I think I found something that moved. Did you find something that moved? Yeah. Were you looking in the same place? Were you looking at a different time? So the AI part is the recognition of something moving slowly over a very long time. But yeah, they go to AI because the AI can do that.
Now, we're looking for planets.
Yes.
I was taught that little stars go twinkle, twinkle. Am I wrong about that?
That's a common misnomer. Planets that are close in, that are very bright, don't twinkle. Stars twinkle. Planets that are very far out, they're very dim, and their light gets distorted by the Earth's atmosphere. So they twinkle.
So if you're looking for planets, they would not twinkle.
No, they would twinkle.
Planets?
Yes, because they're far enough away and they're dim enough that they have the same behavior as stars. So if it's a bright planet or a bright asteroid or comet, those don't twinkle because they're close enough for more of their photon flux to make it into your eyeball or your camera. But when you get farther and farther out in the solar system, there's fewer and fewer pixels. And the signal to noise ratio of the pixels you're gathering varies with distortions in the atmosphere. So if you're looking at something that's only like 6 pixels, they're not 6 pixels across or in a line. It's a kind of a floating blob of about 6 pixels. And the one that's the brightest may not always be the brightest. The one next to it might suddenly be the brightest because the atmospheric distortion changes the pixels you're seeing. So yes, planets, asteroids, comets, typically they don't twinkle, and that's how you can spot them. But once they're far enough out in the solar system, they're dim enough and small enough that they're going to be affected by twinkle.
Yeah, I heard the same thing. I noticed Jupiter and Saturn, they don't twinkle.
Right.
But I guess Uranus would twinkle.
Uranus is, I guess, kind of a borderline case. Pluto would twinkle. Uranus and Neptune, I think they have strong enough light and they're in color that they would be less likely to twinkle. The thing that I've always spotted in the sky that twinkles the most is Canopus, a star from our point of view in Fort Lauderdale, towards the southern horizon. Whenever you look in that direction and Canopus is up there, it looks like a helicopter with a spinning red, green, blue light. Canopus is an extremely bright star, but it's very far away. So the Earth's atmosphere distorts what you're looking at and it twinkles like crazy. Okay, any other comments or questions before I stop recording? Okay, hearing nothing.